open up your VS Code, and we're going to create a new notebook and name it as a Ridge and Lasso regression.ipynb. Once you're done, you let me know. Ridge and Lasso regression.ipynb. Okay, so like I'd mentioned yesterday, so we select a kernel first for this. So like I'd mentioned yesterday, so Ridge and Lasso regression are regularized versions of linear regression, and we'll be having a new parameter coming in here. It's called the alpha. I will start a default one, and I'll show you on how you can determine the best alpha by making use of the cross validation. We'll still be making use of the same dataset, that is the Fetch California Housing dataset, and compare the two results and see when you have a linear, when you have a ridge, and you have a lasso, what's the difference? Is our model improving? And what's the way forward? Okay, and this one will be in regards to you again redoing the whole process. Once you do your EDA and you address the outliers, then you'll be able to see the difference that is in your assignment from the coursework, from the classwork that we haven't addressed all that, and after you address all that. So you'll have the before and after. So we are going to start with the ridge, okay? Or we can have a linear, okay? So we can have a linear, we can have a ridge, and we can have a lasso, and we print all the metrics together. And upon printing all the metrics together, you'll be able to see what is the difference between all of them. Okay. So here we are going to have so here we get to import the necessary libraries. Okay. So here I'm going to import pandas as PD. We'll need to bring in our numpy. We'll need to bring in our train test and split, of course. We'll need now to bring in our data set. So from sklearn, from sklearn dataset, I'm going to import the Fetch California. The Fetch underscore California underscore housing dataset. Then now we're going to bring in our models. So from sklearn dot linear underscore model, going to import the linear regression. We'll bring in our ridge and we'll bring in our lasso. So I'm going to explain all this, and of course the metrics that are associated with regression models. So that is the mean squared error and the R2 score. Then we're going to print that is libraries imported successfully and execute. That's there. Okay. So far, Janet, I'm assuming that you know each and every vocabulary at this point. Huh? that we've just typed in this cell, except for Ridge and Lasso, and what and why we are importing them. Is that clear? Or do you need any clarification on those lines of code?
I think it is okay.
Yes, come again.
I'm okay.
Okay, so
Yeah.
wait for this. It take a bit of some time. Huh? Has yours executed on your end?
Yes.
Okay, so you might some time. Okay, so we have the libraries have been imported successfully, and now let's load our data. So we load the data set. And remember, we're making use of the Fetch California housing, so we need to initialize it. Okay. And in this case, now after initializing it this way, so we'll need now to define the x and the y vector. So we get to define the x and, and the y vector. Now, this data is in form of arrays, like we've seen in our reporting. Okay, so we're here. So I was defining the x and the y vectors, and in this case now, what we're going to go about it is we can decide and just have it direct as a housing.data to go about your x and also the y to be the housing dot target. And also another way whereby you can do it, you can have it as x equals to pd dot data frame housing dot data, then the column names associated with them, that is the housing dot feature names. I've explained this one. Then we can have now our y coming about with the pd dot series can also work, and also the dot data frame, okay, like we did in the previous class yesterday. And once you execute this, everything should work. And even you can check for your X, you'll be able to see a tabular output that is rows and columns because of the association with the pd.data frame. Of course, this is the pandas library uh, coming about with the dot data frame function. Okay, so you can have that. Run all this. Okay, then now we split the data into training and testing sets. So so here again we'll come about with the four variable names, that is the X train, the X test, Y train, and the Y test. Okay. And subjecting it to our X and Y vectors that we've already defined. Uh we define the testing size at 0.2, meaning that we are training at 80, we are testing at 20%. Then for reproducibility, we have a random state of 42 right there. Execute that. Should be a success. So you let me know once you're here, then I can proceed.
Hello?
Yes.
Oh, you can proceed.
Okay. So we're going to train three models. So we'll have the normal linear regression, then we'll have the ridge, then we'll have the lasso. So the normal linear regression is just a replica of what we did yesterday, but now we're doing it again so that we can compare. Are we getting any differences even as much as we do our regularization with our alpha parameter? So we train the normal linear regression model. So the normal linear regression model, you can have it with this variable name, lin underscore reg, or rather you can have it as linear underscore model, easier interpretability. Then you'll have to fit with your data, that is your X train and your Y train. And upon fitting, now we make predictions with the linear regression model. And so we're making prediction based on what we had set aside, that is our X test. Then after doing that, we now evaluate. We now evaluate the model, and are going to make use of the MSE. So I'm going to give it MSE underscore linear because we're going to have multiple. So we'll have MSE underscore linear, MSE underscore range, and MSE underscore lasso. Just for the case of preventing any conflict of the variable names, that is the values that we're storing. Then we have the R squared linear right there. Okay. Now, you can decide and print this at this point here, and you can see what we are getting is what we were getting yesterday. I mean the class before. Yeah, 0.55 for the MSE, 0.57 for the R2 score. Right there. So after doing that, now you need now again to train the ridge regression model. Ridge regression model. And here we're going to have some notes on the same. So what is the ridge regression model? So if we may ask ourselves, okay. So okay. So the ridge regression model, let me have this way. Okay. Now it's a regularization technique. First of all, regularization linear model. That's the first thing that we need to know. Now it makes use of an alpha, and this alpha is part of the parameter that is it's able to act upon a penalty. So it's being referred to as the L2. Okay. So ridge regression is a linear regression plus L2 penalty. So what it does, the coefficients will shrink but remain in the model. So ridge does not remove the features. So what it does, that it adds a penalty to the coefficients to make them shrink but does not remove them. Unlike for the lasso, whereby it removes. Okay. So you can have a point here. So ridge regression model is a linear regularization. Let me remove this. regularization, a technique that adds a penalty equal to the square of the magnitude of the coefficients to the loss function. There is a math behind it. I'll try and I'll look for it and share. So it's usually a math that shows you on how it's adding the square of the coefficient, the magnitude coefficients to the loss function. So why does it do this? So this helps to prevent overfitting by shrinking the coefficients of less important features towards zero. But unlike Lasso, which I've just mentioned, it does not set them exactly to zero, because if it sets them exactly to zero, then it means that you've gotten rid of the features. Then regression is particularly useful when dealing with multicollinearity, when predictor variables are highly correlated in the dataset. So how will you know that they are highly correlated in the dataset? So you'll go about during your EDA. That's why I'm insisting on the EDA. So your EDA will show you, because you'll have the heat map, so you'll be able to see the correlation through the heat map, because you will have plotted uh, and annotated your your coefficient. Okay. So so the ridge, you'll see it will be making use of an alpha, and this alpha by default usually you'll see a 1.0, but you can also try to get the optimal of the 1.0. Now we can have the model. So we'll have ridge underscore model equals to the ridge, which is now what we imported here, this library at the top. Then we're having an alpha of 1.0. Okay, so the alpha is the regularization strength. Then moving forward, now we'll fit it with our X train and our Y train. Okay, the same case we did for the prediction for the linear, we can also do the same, because we need this to determine the evaluation of the model. So we'll do the MSE and the R2. Then we can even also print the same. So you can see here we have a ridge regression. We're getting an MSE of 0.5, and the R squared is at 0.57 right there. Okay. So how do you determine the best alpha? So the best alpha comes about if you do a cross validation. So to determine the best alpha, for the ridge regression. Okay. So the first thing here you need to do is you need to bring about the ridge CV, which is the library responsible for this. So from sklearn dot linear underscore model, we're going to import the ridge CV right there. Then after importing it, you can try to come about with random values of different ranges of your speculated alpha. Okay. Now, when you're coming about with this, also be considerate with the computational power, because the computational power of your machine really determines how long the cross validation will take. So if you have more so when you're making use of VS Code, so if you have a less powerful machine, it will take more time. But for the case of like the likes of Google Colab and any other cloud IDE that handles notebook and the development of models, then you'll have more, because like for the case of Google Colab, you're able to get the premium version of it. Did you do any Google Colab notebooks? when you are doing Python?
No, we didn't.
Okay, I'll take you through Google Colab.
Okay.
So basically, it's a web IDE. Uh, it's a Google product. And all you need is a Gmail account, and of course, your Gmail account is connected to your drive. So you'll be just be creating notebooks the same way we are doing here for VS Code. And upon the creation of the notebooks, you'll be auto saved towards your drive. The good thing about it is you can access the GPUs, the TPUs, the sophisticated ones, but in form of a cloud. Instead of assembling a whole computer just for a small project that you are doing that requires some of those specifications, you can just subscribe and you're able to run very heavy algorithms. So we're going to define our alphas right here. So upon defining our alphas, now we're going now to subject our ridge CV, whereby it will be picking for us the best alpha from it. So we'll have ridge underscore CV underscore model, because now this is the ridge regression model that has been done for a cross validation, and it will be based on the alphas that will be gotten. So it will store the cross validation values, and it will fit to the X train and the Y train. Okay. And so we need to get the best alpha, and for us to determine the best alpha from it, because it will need to retrain as a model, picking the alpha of 0.1, check, the alpha of 1.0, check, the alpha of 10.0, check, and the alpha of 100.0, check. Then it's able to return the best alpha from it. So for you to view the best alpha based on the list that we've just provided, that is the 0.1, 1.0, 10.0, and 100.0, you should be able to print out this, and you get an output. So here we're getting the expected keywords to so this one was updated, so you can go about this. Let me structure that. uh, Alphas. Let me just remove that. Okay, then you can see based on the list we have here 0.1, 1.0, 10.0, and 100.0. The best alpha is 10.0. So it means that if we replace this one, so you can say 10. Let's see if our model will improve. So we can say 10, 10.0. So currently we are doing a 0.55, 0.57. What if we execute? So it doesn't change, but it's saying it's the best alpha. Okay. So those are the some of the issues, and also some of the challenges that you will come about with as an ML engineer when you calculate the best alpha, then again feed back to the model, then again it kind of gives the same metrics. So you trace back to your EDA, okay, and exhaust everything. Any questions so far? Janet, any question?
No.
Okay. So this is for the ridge. So you can have this together. So you can have this. I'm just demonstrating. So you can decide and have this right there, and then uh, have something like this. Print. Okay. So this one. So you print. Uh, Alpha 1.0 and yeah, we can have something like that. Should I give you time to type?
Yes.
Okay, you let me know once you're done.
Okay. Hello.
Yes.
I'm done.
Okay. Okay. So let's do the same for the lasso. So we're going to train the lasso regression model. Okay. So what is the lasso regression model? We're going to have the same here. So lasso regression is a least absolute shrinkage and selection operator. It's a linear regression technique that adds a penalty equal to the absolute value of the magnitude coefficients, the loss function. Okay. So it adds a penalty that is equal to the absolute value of the magnitude of the coefficients to the loss function. And this penalty this penalty term encourages sparsity in the model by shrinking some coefficients to exactly zero, effectively performing variable selection. And lasso regression is particularly useful when we have a large number of features, as it helps to identify the most important predictors and reduce model complexity. So you can have this way. Yeah. Okay. So for the lasso, it goes about the same way. So you have to have the parameter alpha. Then you fit, that is the X train and the Y train. Then you make predictions to the model to determine your Y with the X testing set that we had put aside. Then you got to evaluate the model, determine your MSE, and also determine the R squared. Okay. Then you can print the MSE and the R squared. So once you execute that, so you'll see the MSE is at 0.93 and the R squared is at 0.28. Okay, which is so bad. So let alone we'll see, is it the alpha that is affecting this performance, or it's the data that is not fit for the model. Have that. Then we can proceed and uh, without this. So determining the best alpha for Lasso regression. Okay. So we need to import that. We can have the alphas. So you can decide and stretch these alphas and have multiple. You can have even 0, 0, 1, um, 1.0, 10.0. Yeah. Okay. Then we fit the alphas, we fit the model, and then we print the best alpha again. Okay. So here we can have that. So yeah. So So it's saying the best alpha is at 0.001. Okay. Can try and replace the this with 0.001 and see whether the results are changing. So 0.001. So that is the best alpha being offered. And that's 0.001. And so you can see upon the changing, we are getting a very different value. So our MSE previously was at 0.93. Our two score was at 0.28 with 0.1 alpha, but with 0.001, we're getting a difference of 0.55 for MSE and our two score of 0.57. So it means that the alpha really plays a significant role as a parameter in this case. Is that okay, Janet?
Yes. Hila,
Yes, yes.
I have a question.
Yeah, sure.
When you were using the 0.1,
Mm-hmm.
we add 0.9, and so like what is the, it should not be above 8, or because we've used 0.01, it is 0.9. Why did we change to 0.01?
Okay. Now, when we started with linear regression models, I mentioned that you get to evaluate a good model through the mean squared error and the R squared, right? Now, with this, it simply means that your mean squared error should be as low as possible. Now, usually the results that come out are in form of decimals. Like you can see here, we have a 0.93. So it means that the rate at which our model is making errors is at 93%. Okay. Then for the R squared, it simply shows how best fit the model is to the data. So the R squared should always be moving towards a whole value 1.0. So you can see here we're getting a 0.2. Okay. So 0.2 simply means that it's very, very poor. Okay. So you need to improve this. And some of the things that you need to adjust or rather tune are the parameters. Now, when it comes for the lasso and the ridge, all you get to adjust is the alphas. Okay. So the alpha is the regularization strength that will have to do a penalty based on based on either it's a lasso or a ridge. And for you to determine the best alpha, because you can just guess, and maybe according to your guessing, you think that you're right, but there is a technique, there is a process on how to determine the best alpha. And this is what I've done just down here. So you can see here, to determine the best alpha, I brought about the library responsible for determining the best alpha, which is the Lasso cross validation. You can see here. Then I started by giving a list of my randoms, okay, that I want to check. So I have 0.001, I have 1.0, I have 10.0, I have 100. So out of this, which one will merge as the best alpha? And of course, the best alpha should also be reflected directly to my evaluation results, which I expect a better MSE, I expect a better R squared. Now, upon doing that, so you have the lasso underscore CV underscore model. So you have the lasso CV, the alphas will be subjected to that. Then I'll fit with the X train and the Y train. Then from here, I'm able to tell the best alpha it as 0.001. And when I come to the alpha and replace that value by having 0.001 and execute, you can see we are having a difference. So you can see we're having a 0.55 and a 0.57. So that's why it's changing. And you can't know the best alpha unless you go about the cross validation. because it will be determining the best alpha based on the fitting with the data. Is that okay?
Yes.
Yeah. Okay. So so you can have a comparison of the results. So uh you can compare the results here from the top. Compare the model results. Okay. So for the comparison of the model results, so we'll have to print for the linear regression, we'll have to print for the ridge, we'll have to print for the lasso here, and we're able to tell so which one is doing better. So from my observation, I can see all of them they're average. Okay, they're not so good, they're not so bad. So depending on how well you'll do your EDA, how well you understand the data, uh, how well you clean the data, how well you address the outliers, we'll be able to tell if these metrics will improve right here. Is that okay?
Yes.
Yeah. So work on the EDA, then send it to me. I'll go through it, then I'll give you my feedback.
Okay.
Yeah.
You forgot to send the
So
PDF.
I had a playlist, so let me show you. I've had a playlist for our class. So I'll just send you the link for the playlist, then you'll be able to go through that.